What does Venus hide? Today, we set off for a world of fire and mist, where clouds are acidic and the ground burns relentlessly. Venus. More than a planet, a twin sister turned stranger. Since the poets of antiquity to the probes crushed by its heat, it troubles, it resists, it enchants. What do we really know about this veiled goddess? And why, among all the lights in the sky, does this one obsess us since forever? But before we embark on a new adventure, don't forget to like the video and subscribe to the channel so you won't miss anything. Thank you, and have a good trip. Since the origins of humanity, Venus holds a unique place in the sky, captivating every civilization that observes it. Around 2,000 years before our era, the Babylonians were already tracking this brilliant star, which they considered an essential celestial guide. In the famous tablets of Ammisaduqa, it is revealed that their agricultural calendars depended on the synodic cycle of Venus, lasting about 585 days. This cycle corresponds to the time it takes for the planet to return to the same apparent position in the sky relative to the sun. The Babylonians thus adjusted their cereal sowing based on the morning or evening brilliance of the star, optimizing their harvests. In ancient Egypt, Venus was associated with the goddess Ishtar, a symbol of love and fertility. Later, the Greeks named her Aphrodite, and the Romans, Venus, perpetuating the image of beauty and passion. A legendary Greek scholar, Pythagoras, was one of the first to understand that the morning star, Phosphoros, and the evening star, Hesperos, actually referred to the same star. This revelation, against the beliefs of the time, marked a significant advancement. This intersection of perspectives among civilizations demonstrates the evocative power of Venus and its ability to inspire the quest for celestial order. The interest in Venus wasn't limited to the ancient world. Among the Mayans, the Dresden Codex contains a remarkably accurate Venus table. Over a period of nearly 2 millennia, their calculations deviated from astronomical reality by only 1 day. Such precision reflects an acute sense of observation. Notable for any sky enthusiast, Venus never appears in the middle of the night, even at the equator. This is explained by its orbital proximity to the Sun, which forces it to never stray too far from our star. It remains visible only at dawn or dusk. From the 2nd to the 15th century, Venus continued to feed scholarly and mystical traditions. In India, the Surya Siddhanta Treaty already proposed complex tables integrating the inclination of its apparent path. Later, the astronomer Al-Battani refined this data by adjusting the planet's latitude, revealing that it slightly deviates from the ecliptic. In China, as well as in the Islamic world, Venus became a bearer of celestial signs announcing terrestrial events. However, the instruments of the time did not yet allow the discernment of its phases. It appeared as a bright disk, without understanding the intensity variations linked to its orbit. The year 1543 changed the course of the history of astronomy. Copernicus published his major work, establishing that the Earth revolved around the Sun. This revolution took shape in 1610, when Galileo, equipped with his telescope, observed the phases of Venus. He noted that its brightness varied like that of the Moon, thus proving that the planet revolved around the Sun. This observation confirmed the heliocentric model and provoked strong reactions. In 1631, Kepler predicted the passage of Venus in front of the Sun, a rare event. Cassini managed to time it, adding an essential data point to the study of orbits. In the Baroque era, these discoveries sparked debates and reflections. Some saw it as a threat to established dogmas, while others tried to reconcile science and faith. salons filled with animated discussions about humanity's place in the universe. Was it merely a celestial light, an inhabited world, or a sphere obeying unknown laws? The study of Venus awakened fundamental questions, suggesting that science could broaden the spiritual vision of the world. Between 1660 and 1800, the transits of Venus became a central issue for astronomers. In 1716, Edmund Halley proposed a novel method, timing the passage of Venus from different points on the planet to deduce the distance between the Earth and the Sun. This ambitious gamble led to epic expeditions. Among the famous expeditions were that of Captain James Cook in the Pacific, those led by Guillaume le Gentil despite heavy setbacks, and the mission of Abbé Chape d'Auteroche. All were driven by the same interest, a few minutes of precious observation. Their combined efforts set the average distance to the Sun at about 153 million kilometers, or 95 million miles, a fundamental milestone of modern astronomy. Thus, from the early Babylonian observations to the great campaigns of the 18th century, the history of Venus reflects the persistent desire to understand the cosmos. Initially perceived as a double star, then integrated into increasingly precise models, it served as a guiding thread in the evolution of astronomical thought. The Copernican model gave it its true place. The phases observed by Galileo validated this vision, and the transits studied using Halley's method allowed the measurement of space with new precision. Venus, once a simple bright point, became a key to understanding the universe. It embodies humanity's journey toward a broader knowledge of the sky. Entering the 19th century marked a decisive step in the study of Venus, driven by the emergence of giant telescopes and new observation methods. Astronomers, fueled by boundless curiosity, pointed their instruments at this familiar bright point in the sky, convinced that Venus concealed valuable clues to understanding the history of the solar system. The rapid progress in optics allowed for broader lenses and more precise targeting systems. Imposing observatories took shape in Europe and North America, each harboring the ambition to unravel the mysteries of the enigmatic glow of this planet, often described as Earth's twin. Some saw it as the key to a common origin between the two celestial bodies, supported by their similarity in size and mass. This dynamic of scientific exploration reflected the intellectual drive of an era eager for answers, fueled by a deep desire to broaden the understanding of the cosmos. The development of telescopes equipped with larger mirrors radically transformed our view of Venus. These new instruments made it possible to hope to discern features on the blinding disk of the planet, although its persistent cloud cover remained difficult to penetrate. The observatories of Greenwich, Pulkovo, and Paris were among the most advanced, equipped to conduct these cutting-edge observations. Each moment spent at the eyepiece sparked the hope of discovering an unprecedented nuance, a variation in brightness, or a subtle detail revealing a surface feature. Despite the opacity of its atmosphere, exchanges among researchers multiplied. Drawings and notes circulated, and discussions intensified around hypothetical seasons, seeking order behind the apparent uniformity. This period saw the birth of a more methodical and collective approach, where contemplation gave way to a truly coordinated study strategy. The arrival of spectroscopy in the 19th century introduced a major advance in the analysis of Venus. This technique consisted of breaking down the light reflected by the planet to extract chemical signatures. By studying these colored lines, T. Slifer highlighted a strong presence of carbon dioxide, composed of carbon and oxygen. This discovery surprised specialists, revealing an atmosphere very different from that of Earth. Already some envisaged that this gas could trap heat, laying the foundations of a greenhouse effect that future research would confirm. This revelation paved the way for a new vision of the planet, more complex and less hospitable. At the same time, Giovanni Schiaparelli became interested in the rotation of Venus. Through the observation of slight variations on its disk, he concluded that the planet rotated very slowly, possibly partially synchronized with its revolution around the Sun. He deduced that a Venusian day was of extreme length, capable of creating striking contrasts between light and darkness. This scenario suggested a climate with marked extremes, raising the question of how potential forms of life could adapt to such an environment. This portrait of a planet subjected to luminous and thermal tensions fueled fascination, inviting people to imagine it as profoundly different from the terrestrial world. The dense and hot atmosphere of Venus sparked all kinds of speculations. Its proximity to the Sun and its sustained brightness evoked a world covered in thick mists, traversed by a diffuse and constant light. Some imagine this thick cloud cover as a suspended ocean, bathing tropical landscapes. Stories were populated with humidity-saturated jungles, immense ferns, and strange creatures evolving in constant warmth. The idea of a dynamic ecosystem, shaped by rapid evolution under the influence of heat, appealed to both scientists and dreamers. Venus became an imaginary laboratory, where nature would have pushed its possibilities even further. This vision, both poetic and scientific, also took hold in popular culture. Illustrated manuals showed mysterious landscapes, bathed in filtered light, populated with silent forests and still lakes. The representations were based on the idea that the abundance of water should lead to original life forms adapted to a perpetually humid environment. Some spoke of flying or semi-aquatic animals, evolving in a closed world, saturated with vapor. The hypothesis of intelligent species also circulated, with the idea of structures, cities, even civilizations, invisible to the naked eye. Venus then became much more than a planet, a backdrop for mental exploration, a space where science met collective imagination. Fiction authors quickly seized upon this fascination. Jules Verne, famous for his terrestrial and lunar explorations, mentioned through his stories the idea of worlds teeming with life, bathed in a rich and warm atmosphere. H.G. Wells, on the other hand, gave his novels a more unsettling scope, describing oppressive and perilous planets. Through these stories, the public imagined Venus as a possible refuge, a parallel territory populated with conscious species, both familiar and foreign. Literature emerged as an extension of the scientific debate, offering multiple visions of a world still inaccessible, but already intensely alive in the minds of readers. By the end of the 19th century, the image of a lush Venus had taken root in the collective imagination. The technical limitations of the time, combined with the overflowing enthusiasm of astronomers, maintained this illusion of a tropical paradise enveloped in clouds. Yet even the first spectral data hinted at a much less welcoming reality, marked by an unbalanced chemical composition. Despite this, the idea of a hospitable planet persisted, fueled by discussions of its slow rotation, the supposed presence of water, and the possible existence of abundant life. This myth, between science and fantasy, marked an entire generation of observers and readers. Before space probes came to extinguish these romantic visions, this period remained a pivotal moment where scientific spirit coexisted with bold imagination. It remains today a vibrant testimony of the intellectual drive that would give birth to modern planetology. Between 1961 and 1970, the exploration of Venus took a decisive turn thanks to ground radars and the first space missions. Until then, the planet remained an enigma, masked by a dense atmosphere, making its rotation difficult to measure. In 1961, the Goldstone site in the Mojave Desert used a radar signal to probe the surface of Venus. Stunning result, the planet rotates in the opposite direction and takes nearly 243 Earth days to complete a full rotation. This revelation challenges the idea of a twin to Earth, as such slowness and direction of rotation defy established models in the solar system. The surprise is immense and inaugurates a phase of intense research. The following year, Mariner 2, launched by NASA, becomes the first spacecraft to fly by another planet. Its sensors detect infrared and microwave emissions, revealing a surface temperature nearing 450 degrees Celsius, or 842 degrees Fahrenheit. The image of a lush planet, covered with tropical forests, collapses. Beneath the opaque clouds reigns an extreme greenhouse effect, fueled by an atmosphere almost entirely composed of carbon dioxide. This discovery, as unexpected as it is brutal, upends the models of planetary habitability. The overwhelming heat and crushing pressure hint at the technological challenges to overcome for a landing to be considered. At the same time, the Soviet Union begins an ambitious series of missions called Venera. The goal, to design probes capable of traversing the dense atmosphere of Venus and, if possible, to touch the ground. The first attempts are inconclusive, but in 1967, Venera 4 manages to penetrate the atmospheric layers and transmit crucial data. It detects an atmosphere largely dominated by carbon dioxide and a much higher pressure than expected. Although it does not survive reaching the ground, this breakthrough proves that exploring the lower layers of the atmosphere is conceivable. Engineers then redouble their efforts to strengthen the thermal shields and improve cooling systems. In 1969, Venera 5 and Venera 6 take over with optimized equipment to gather more information during the descent. They measure variations in pressure, temperature, and the chemical composition of the air. Despite these improvements, they succumb before reaching the surface. The environment remains unforgiving. Enormous heat and pressure destroy the internal components. Yet, each transmission illuminates Venus's complexity a bit more. Scientists begin to understand the stability of the winds according to altitude and confirm the omnipresence of carbon dioxide. Venus now appears as a gigantic furnace where the survival of machines is an achievement. Then, in 1970, Venera 7 accomplishes the unimaginable. It lands on the Venusian soil. Designed from lessons learned from previous attempts, the probe is equipped with robust shielding, a pressurized compartment to protect the electronics, and a parachute adapted for a long descent. Upon entering the atmosphere, it faces extreme heat and monumental pressure, but manages to function for a few moments after landing. This brief signal marks a world first. For the first time, data comes directly from the surface of such a hostile planet. This success validates the Soviet approach and opens a new chapter in the exploration of Venus. The feat of Venera 7 causes a resounding shock. It demonstrates that a craft can withstand extreme conditions, even briefly, and transmit information from the surface. Buoyed by this success, the Soviets assert their role as pioneers of planetary exploration. In the United States, the advancements are closely monitored, but attention remains focused on the Apollo lunar program. Nevertheless, interest in Venus grows within the scientific community, fascinated by this planet so close, yet so different. Its slow rotation, infernal atmosphere, and extreme temperatures fuel new hypotheses about the divergent trajectories of Venus and Earth. The foundations of comparative exploration are being laid. Beyond the technical feats, this decade marks an awareness of extreme climatic phenomena. The greenhouse effect observed on Venus, caused by the accumulation of carbon dioxide, illustrates the ability of a gas to radically transform a climate. This Venusian lesson echoes growing questions about the terrestrial industrial impact. Thus, the study of Venus goes beyond space conquest. It challenges astrophysicists, geologists, and ecologists. By comparing the two planets, scientists seek to understand why one became uninhabitable while the other could host life. The reversed rotation, air density, and presence of sulfuric acid offer as many leads to understanding this divergence. Ultimately, the period from 1961 to 1970 illustrates human audacity and perseverance in the face of a formidable planet. From the discovery of a retrograde rotation to the recording of scorching heat, and through the daring descents of the Venera probes, each stage pushes the boundaries of knowledge. With Venera 7, exploration takes on a new dimension. It is now possible to touch the ground of a world once deemed inaccessible. The adventure is only just beginning. The decade ending in 1970 unveils a new face of Venus. Far from past speculations, we discover an overwhelming world dominated by unbearable heat and crushing pressure. Thanks to radars and probes, a backward rotation is identified, a powerful greenhouse effect, and the possibility, albeit brief, of a landing. These first steps mark the beginning of a greater ambition. Between 1961 and 1970, humanity takes a major step forward and lays the groundwork for a Venusian exploration essential to our understanding of our own planet. From 1972 to 1985, Venus becomes the stage for a major new episode. The Soviet Union and the United States engage in audacious missions there, hoping to better grasp the nature of its scorching atmosphere and tumultuous surface. The infernal conditions, such as 470 degrees Celsius or 898 degrees Fahrenheit, and a pressure about 90 times that of Earth, demand engineering feats. The Soviets continue their Venera program, this time to analyze the soil composition. The Americans, for their part, develop Pioneer Venus, dedicated to studying the atmosphere and topography hidden beneath thick clouds saturated with carbon dioxide. Gradually, these efforts reveal a volcanic world as fascinating as it is hostile. The Venera missions initiated earlier paved the way for an unprecedented milestone. In 1975, Venera 9 and Venera 10 transmit for the first time images taken from the Venusian surface. After descending through corrosive clouds, each module lands smoothly. The devices survive only a few dozen minutes at a temperature of more than 460 degrees Celsius or 860 degrees Fahrenheit and an almost unbearable pressure. This short window is enough to send photographs of an arid landscape strewn with basaltic rocks. Thanks to a specially designed porthole, the cameras offer a glimpse of a scattered ground, with angular shapes covered in a fine dust. These images compose the first real vision of this overwhelming world. In addition to the pictures, the instruments of Venera 9 and 10 analyze atmospheric gases and confirm the dominance of carbon dioxide, accompanied by traces of other elements. This gas, responsible for the intense greenhouse effect, traps heat to the point of melting lead. The probes also detect sulfuric acid in the clouds, formed by chemical reactions between sulfur and oxygen. The recorded pressure variations indicate a surface far from homogeneous, prompting researchers to devise new topographic analysis methods. Although their lifespan is brief, these missions prove that it is possible to land and operate on an extreme planet. They paved the way for even more in-depth explorations, aimed at Venus's internal structure and mineral composition. In 1982, the Soviet Union launched Venera 13 and Venera 14. Equipped with sophisticated instruments, these probes study soil composition and capture color images. Their panoramic cameras, reinforced to withstand extreme conditions, transmit impressive views of the surface. The density of the atmosphere alters the light, giving the images a yellowish tint. Designed to withstand a pressure equivalent to 90 times that of Earth, the devices reveal a plain, strewn with rocks and basaltic fragments. The integrated drills collect samples analyzed on site. The results, published by the Planetary Society, confirm the presence of rocks similar to those of Earth's ocean floors, suggesting intense past volcanic activity. Although short-lived, the missions of Venera 13 and 14 remain a major reference for understanding Venusian geology. In the United States, the Pioneer Venus mission began in 1978. It consisted of an orbiter and several descent modules. The orbiter followed a polar trajectory to measure the atmosphere and magnetosphere over the long term. The multi-probe modules, dropped at different latitudes, penetrated the thick clouds to gather data on density, temperature, and chemical composition. Some sensors revealed violent winds, highlighting an atmospheric superrotation. The air circulates around the planet in just a few days. This particular dynamic, combined with an intense greenhouse effect, intrigues scientists who seek to understand the mechanisms at play. Pioneer Venus also made it possible to establish a large-scale map for the first time, highlighting extensive volcanic regions and high plateaus like Ishtar Terra. The onboard instruments detected topographical irregularities, including Maxwell Montes, the highest point, which rises several kilometers or miles. Through radar surveys, researchers identified areas called tesserae, with complex and intertwined geological patterns. These formations resemble a mosaic of ridges and faults, possibly indicating an active tectonic past or an ancient reorganization of the crust. The descent probes confirmed the dominance of carbon dioxide in the atmosphere and the presence of acids in the clouds. The modules ceased functioning shortly after their readings, crushed by the extreme conditions. Pioneer Venus, completed in the mid-1980s, brilliantly complemented the discoveries of the Venera missions by broadening our vision of Venus. The period from 1972 to 1985 clearly illustrates human determination to push technological boundaries to explore one of the most hostile worlds in the solar system. The Venera missions proved that landing on a scorching surface exceeding 400 degrees Celsius or 752 degrees Fahrenheit could produce valuable data. The cameras revealed a volcanic landscape, and the sensors confirmed the omnipresence of carbon dioxide. On the other hand, Pioneer Venus highlighted the diversity of the terrain, analyzed the winds, and revealed the mysterious tesserae, suggesting a dense geological past. Thanks to all these missions, Venus is envisioned as an extreme example of planetary evolution dominated by an overwhelming greenhouse effect. Venera demonstrated Soviet technological robustness, while Pioneer Venus emphasized the importance of mapping. Together they laid solid foundations for our understanding of this veiled planet. Between 1985 and 1994, two major missions helped unlock the mysteries of the Venusian surface: Vega 1 and Vega 2 on the Soviet side, and then Magellan on the American side. Vega 1 and Vega 2 were launched in the mid-1980s. Their main objective, to release a balloon in the atmosphere of Venus at an altitude of about 55 kilometers or 34 miles. At this height, The pressure and temperature are more moderate, offering favorable conditions for studying the winds. These balloons, designed to float for an extended period, recorded the first direct data on atmospheric circulation. Scientists observed zonal winds moving from west to east along a broad band near the equator. The measurements revealed speeds of several hundred kilometers or miles per hour, illustrating a super-rotation far exceeding the planet's own rotation. A Venusian day extends over months, while the atmosphere completes its circuit in just a few days. In parallel, the Vega probes collected data on the composition of the clouds, rich in sulfur dioxide and sulfuric acid. These analyses provided a valuable glimpse into a world where pressure crushes and temperature approaches 470 degrees Celsius or 878 degrees Fahrenheit. Vega marked the pinnacle of the Soviet program dedicated to Venus. At the same time, NASA embarked on an unprecedented mapping mission. Magellan left Earth in 1989 and reached Venusian orbit the following year. Its mission, to create a nearly complete map of the surface using high-resolution radar. This radar system emits radio waves that bounce off the ground and are captured on return. It allows seeing through the thick and persistent clouds. While this technique had been used before, it had never achieved such precision or coverage. Magellan followed a polar orbit, flying over the north and south poles with each rotation. Thus, it gradually scanned the entire planet. By the end of the mission, it had observed nearly 98% of the surface, offering an unprecedented view of this scorching world. The images reveal a landscape dotted with volcanic structures. Thousands of volcanoes appear, some a few kilometers or miles across, others exceeding 100 kilometers or 62 miles. Among the most striking formations are the coronae, vast geological rings surrounded by circular fractures. These coronaes are caused by the rising heat from the mantle, which deforms the crust at the surface. This creates a dome, sometimes cracked in concentric patterns. Frequent on Venus, they are rare on Earth, reinforcing the idea of a volcanism peculiar to this planet. Through these observations, Magellan questions the idea of a geologically inactive planet. Volcanologists scrutinize each image for signs of eruptions or recent flows. While no current activity is formally detected, the density of volcanic reliefs testifies to a tumultuous past. The maps also reveal vast lava plains, high plateaus, and few impact craters. The thick atmosphere and volcanism seem to erase the traces left by meteorites, unlike the Moon or Mercury. By analyzing the topography, researchers discover elevated regions comparable to Earth's continents. Ishtar Terra, in the northern hemisphere, reaches altitudes equivalent to Everest. Aphrodite Terra, larger, stretches near the equator, unveiling still mysterious mountains. One of Magellan's major advances is the measurement of crust density, obtained by cross-referencing gravitational data and radar images. This method allows estimating the crust's thickness and the distribution of internal materials, refining models of the planet's deep structure. As data flows in, a debate ensues. Has Venus's surface recently been reshaped by massive volcanic events? Some propose that this renewal occurred a few hundred million years ago. Others suggest a still active, but subtle, volcanism. Magellan thus rekindles interest in the geodynamics of Venus. Scientists question the effects of the absence of water, which on Earth plays a key role in plate tectonics. On Venus, without water, the dissipation of internal heat might follow a completely different path via violent volcanic episodes. question remains, is the planet still active today? Magellan's instruments cannot detect heat or emitted gases, only the relief. Thermal or spectroscopic sensors would have been needed to achieve this. Despite this limitation, Magellan radically transforms our perception of Venus. Long considered a sterile twin of Earth, shrouded in an opaque cloud mantle, it reveals an unsuspected geological richness. Magellan's surveys inspire simulations exploring its evolution. Some models suggest it was once temperate, before carbon dioxide caused its climate to tip over. Magellan paves a new path for studying this burning world. (1998) marks a turning point in the exploration of Venus. A new phase begins, based on flybys by probes initially intended for other planets. Often relegated to the role of a simple passage point, Venus nonetheless becomes an essential cog in the spatial mechanics. Its attraction is exploited to adjust the trajectories and speeds of spacecraft, while saving fuel. At first glance, the planet does not seem at the core of the objectives, and yet it provides valuable data on its own atmosphere, notably on a baffling phenomenon, the superrotation, a movement where the dominant winds far surpass the planet's slow rotation. At the end of the 1990s, the Galileo probe, launched by NASA to study Jupiter and its moons, was nearing the end of its long journey. Since its launch at the end of the previous decade, it had engaged in several flybys to reach its destination. Even once it arrived in the vicinity of Jupiter, it continued to send usable calibration data to better understand the spectral characteristics observed in the inner solar system. Although its passage near Venus dated back to 1990, the analyses continued until 1998, allowing comparisons between findings made near Jupiter and those collected around Venus. This comparison created an essential scientific link, validating instruments and providing points of comparison on atmospheric chemistry. Thus, the data gathered on reflected light and cloud composition provided initial clues about the dynamics of the high Venusian atmosphere. Between 1998 and 2005, another mission drew attention, the Cassini probe. Resulting from an international collaboration, it was designed to explore Saturn, its rings, and its moons, notably Titan. To reach it without wasting energy, Cassini followed a complex path through the solar system. Venus played a crucial role here. Two close flybys in 1998 and then 1999 allowed the probe to adjust its speed and continue its journey toward the Saturnian reaches. But these flybys were not limited to orbital maneuvers. Cassini activated several instruments to observe the light emitted by Venus, especially on the night side, invisible from Earth. Using infrared sensors, it detected heat escaping from the lower layers of the atmosphere. Observing this dark side from our planet is difficult, as sunlight blurs the weak signals. However, in close orbit, Cassini could capture thermal emissions at specific wavelengths where clouds become partially transparent. This method, called night-side infrared observation, revealed varied thermal profiles. The measurements confirmed the presence of an atmosphere dense with carbon dioxide, a gas that traps heat and creates an extreme greenhouse effect. Subtle variations in cloud brightness also indicated that the winds were circulating faster than previously thought. As the mission progressed, the contours of superrotation became clearer. Venus spins very slowly and in the opposite direction to most other planets. Where Earth completes a rotation in 24 hours, Venus takes about 243 days. Yet, its high-altitude clouds complete a full revolution in only 4 Earth days. This striking contrast reveals an atmosphere moving much faster than the surface, justifying the use of the term superrotation. Already suspected from the first radar findings of the 20th century, this phenomenon found a brilliant confirmation thanks to data from the probes of the late 1990s and early 2000s. In 2000, Cassini moved away from Venus, making way for a new mission, Messenger. Tasked with exploring Mercury, this American probe was launched in August 2004. To slow down sufficiently and enter orbit around the first planet of the solar system, it needed to utilize several planetary flybys. Without these gravitational adjustments, it would be flung towards the Sun. Venus thus became a necessary stop. Even though the detailed study of this planet was not its priority, Messenger took advantage of every opportunity to gather data. From 2004 on, simulations were conducted to calibrate the instruments and optimize observation conditions during the flyby. One of the major focuses of this work was measuring the rate of superrotation. By observing the clouds through certain infrared wavelengths, underlying structures were identified. Their movement in the Venusian sky made it possible to evaluate wind speeds. When compared to the slow rotation of the surface, a spectacular difference was noted. The high atmosphere completes a full revolution in about 4 days. The observations of Messenger, although secondary in the mission, confirm the results obtained by previous probes. These rapid flybys, far from being anecdotal, are essential. With each pass of a spacecraft, instruments are tested, data is cross-referenced with previous archives, and new avenues for analysis are opened. The readings from Messenger add to those from Cassini and Galileo, forming a coherent set. Venus then becomes a natural laboratory where one can study extreme dynamics, a crushing pressure at the surface, violent winds at altitude, and an atmosphere that defies intuition. Each pass, each measurement, enriches our understanding of this unique super-rotation in the solar system. Between 1998 and 2005, the idea that Venus harbors an ultra-fast moving atmosphere gains strength. This finding is intriguing. How can such a slow planet harbor such a dynamic atmosphere? With temperatures over 450 degrees Celsius or 842 degrees Fahrenheit at the surface, the Venusian world remains inhospitable. But as one ascends in altitude, the temperature drops. It is about 50 kilometers or 31 miles above the ground that the balances play out. It's there that winds sculpt clouds and redistribute energy. Galileo, Cassini, Messenger. 3 probes, 3 decisive flybys. By collecting infrared data on the night side of Venus, they demonstrate the vigor of its atmospheric circulation. Observing this heat emitted in darkness requires extremely sensitive sensors. Cassini manages it, and Messenger does too, to a lesser extent. Together, their observations sketch a thermal portrait of the planet, based on far infrared. These missions also revealed a tremendous opportunity, studying multiple planets with a single device. Interplanetary voyages are costly. To limit expenses, trajectories are devised to take advantage of gravitational fields encountered along the way. Venus, with its significant mass, allows these adjustments. And since the probe passes nearby, why not take the opportunity to observe? With each flyby, the scientific file on superrotation is enriched, revealing the impressive speed of winds in the high atmospheric layers. The years 2003 to 2005 are intense in preparation. Messenger approaches Venus for a first critical maneuver. Teams refine flight parameters and ensure the instruments are ready. Although designed for Mercury, some can offer valuable observations on Venus. Superrotation remains at the heart of expectations. Scientists hope to refine measurements and confront them with previous data. In light of this period, Venus stands out as a centerpiece of space exploration. Even when it is not the main objective, it becomes an unavoidable passage. Much more than an orbital springboard, it is a world apart, shrouded in carbon dioxide, bristling with sulfuric acid clouds, where winds race around the planet in 4 days. An atmosphere in fury on an almost motionless surface. Thanks to these modest flybys between 1998 and 2005, this secret has turned into scientific truth. Thus, the infrared measurements, the validation of the superrotation phenomenon, and the clever use of gravitational assists show the full intelligence of interplanetary missions. On the way to other worlds, they steal from Venus some of its mysteries. This groundwork has paved the way for more in-depth orbital research, and it is a reminder that Venus, far from being a failed twin of Earth, remains an enigma in itself, understanding which requires patience, method, and renewed attention. In 2006, the European Space Agency placed a probe named Venus Express in orbit around Venus. Designed to explore the planet from multiple angles, this mission quickly revealed the unsuspected complexity of its atmosphere and internal dynamics. From its launch until the end of its mission in 2014, Venus Express observed the planet tirelessly. It alternated high-altitude flybys with phases of close observation, during which its instruments analyzed the composition of the air, winds, temperatures, and detected any traces of volcanic activity. For a public not initiated into space exploration, this probe has truly transformed the image of the twin sister of Earth, so nicknamed because of its similar size and mass. However, it must first be emphasized that entering orbit around Venus is a technical feat. Located closer to the Sun than Earth, this planet subjects any spacecraft to increased exposure to heat fluxes and solar radiation. This extreme environment poses a real challenge for solar panels and thermal regulation, with onboard electronics needing to remain well below 50 degrees Celsius, 122 degrees Fahrenheit. Nevertheless, Venus Express manages to maintain continuous operation thanks to an ingenious thermal system and precise energy management. Although inspired by Mars Express, a mission to the Red Planet, it has been greatly adapted to withstand the scorching conditions of Venus's vicinity. Upon its arrival in spring 2006, the scientists' priority is clear: to study the atmosphere. A first major discovery concerns a phenomenon at the South Pole, where an immense vortex reigns in the upper layers of the air. Before this mission, the presence of a polar vortex was suspected, but its structure and evolution were unknown. Venus Express then reveals a double vortex, two massive, nearby, and changing atmospheric spirals. The existence of these two centers of rotation immediately intrigues. Why two, and not just one? On Earth, polar cyclones are known, but rarely with such stability and in this double form. In simple terms, this phenomenon called superrotation is explained by the interaction between the rapid rotation of the upper atmosphere and the uneven heating of the pole by the sun, combined with internal wind movements. This superrotation causes the high atmosphere to circle the entire planet in just 4 Earth days, even as Venus rotates very slowly on its axis. Among the onboard instruments, an infrared camera and a thermal spectrometer reveal the atmospheric layers and closely monitor this double vortex. Temperature differences between the spirals, which can reach several tens of degrees, reflect gas mixtures and variations in sunlight. Venus does not experience seasons in the terrestrial sense, as its tilt is nearly zero. Therefore, it is the variations in orbit and the duration of the mission that allow observing changes in the vortex, sometimes merged, sometimes well separated. In parallel, the mission closely examines the chemical composition of the atmosphere. One gas particularly attracts attention: sulfur dioxide. The Venusian atmosphere is dominated by carbon dioxide and nitrogen, but notable traces of sulfur dioxide are also detected. This gas shows astonishing variability over time, which intrigues scientists. On Earth, it is often linked to volcanic activity. Its fluctuating presence on Venus could indicate recent activity. Other explanations are considered: photochemical reactions due to the sun, or vertical movements in the atmosphere that would move the compounds. Venus Express observes unexplained drops and increases in its concentration. Several hypotheses emerge. Eruptions could inject sulfur dioxide at high altitude before the atmospheric chemistry transforms or disperses it. This finding rekindles an old question: is Venus still volcanic? The collected data provides strong hints without formal proof. Another major advancement: the detection of thin layers of ozone at high altitude. On Earth, this molecule, formed of 3 oxygen atoms, protects the surface by absorbing ultraviolet rays. On Venus, the quantities are much smaller, but their presence remains crucial for understanding planetary chemistry. The SPICAV instrument detects these layers around 100 kilometers, 62 miles in altitude. Unlike Earth, Venus has neither vegetation nor abundant free oxygen. Ozone forms there through different mechanisms, notably the dissociation of carbon dioxide by solar radiation. Studying this molecule thus provides insight into the complex chemistry of a planet without a biosphere. Gradually, other clues accumulate. Some suggest that lightning might strike the Venusian atmosphere. Before Venus Express, the signals were too weak or ambiguous. This time, thanks to more sensitive instruments, the probe detects electromagnetic emissions consistent with electrical discharges. In the dense sulfuric acid clouds located at high altitude, storms could thus be possible. The question remains open: are these lightning strikes frequent or occasional, limited to certain regions, or widespread? In any case, this possible electrical activity brings Venus a bit closer to Earth, or even to Jupiter, famous for its violent storms. One of the most remarkable observations concerns volcanic flows. Under its thick cloud cover, Venus remains invisible to conventional cameras. Infrared thus becomes a valuable tool. Venus Express scans the surface looking for hotspots, areas where the temperature rises slightly. Detecting these sometimes minute differences in an already scorching environment requires extreme precision. The data reveals several suspect areas, interpreted as evidence of volcanic activity. On Earth, lava also emits in the infrared. Although no eruption was directly filmed, these results suggest moderate but recent activity, a discovery that changes the image of a planet once thought to be geologically dormant. Several elements converge: sulfur dioxide at high altitude, thermal anomalies on the surface, and some geological formations compatible with recent flows. If Venus is still active, this challenges our understanding of its evolution. Internal heat escapes mainly through volcanism, and the super-rotation of its atmosphere could even be fueled by this internal energy. Between 2006 and 2014, Venus Express collected an impressive amount of information, raising new questions. Was the planet more temperate in the past? Did water vapor play a major role? Could ancient oceans have influenced its chemistry before the runaway greenhouse effect took over? During these 8 years, scientists analyze each thermal and spectral data point. The false color images reveal a complex world: shield volcanoes, basalt plains, circular structures formed by magma pressure under the crust. On Earth, a satellite would easily capture volcanic plumes. On Venus, one has to read between the lines, or rather, between the clouds. Thanks to infrared, Venus Express manages to pierce this veil and offers an unprecedented portrait of a world in turmoil. In the last months of the mission, the probe lowers its orbit to skim the upper layers of the atmosphere. It measures the density and composition there to better understand the escape of gases into space. The fuel is running low, and the end is near. But the scientific yield is immense. Double vortex confirmed, sulfur dioxide mapped, ozone detected, lightning evidence observed, and thermal signatures of possible volcanism identified. This profusion of discoveries inspires new missions focused on atmospheric chemistry, volcanism, and possibly even the potential for habitability in the cloud layers. Throughout the mission, the rigor is total. Each anomaly is checked, compared, confronted with models, whether chemical, dynamic, or thermal. The Venusian system is rarely complex, and each clue is weighed carefully. Crushing pressures, extreme temperatures, blistering winds, corrosive clouds. Venus is a radically different world that demands patience and method. Around 2010, discoveries multiply. Conferences abound, articles flourish in scientific journals, and images captivate. Unlike the intermittent shots from the Venera probes, Venus Express offers continuous observation spread over nearly 8 years, an unprecedented wealth in the exploration of another planet. Comparisons with other missions, including those briefly passing through Venus, further reinforce the impact of this European adventure. In the very last stages, engineers conduct controlled descent tests. The goal, to better understand the friction forces for future probes capable of exploring the clouds more closely. Although the link with Venus Express is broken in 2014, its instruments have operated beyond expectations. The double polar vortex remains one of the most striking images, 2 giant spirals seeming to peer into the depths of the South Pole. Between 2006 and 2014, Venus Express profoundly transforms our understanding of the hottest planet in the solar system. Vortices, changing gases, ozone, lightning, volcanic traces. This puzzle reconstructs a fascinating world. Whether one is an expert or just a fan, it's hard not to be dazzled by a world that is both close and radically different. And the questions raised don't stop there. Other missions continue the momentum, delving into the scientific legacy left by Venus Express. This probe proved that a planet, even one familiar and nearby, can still surprise us. And that space exploration, when sustained over time, reveals unsuspected wonders. As its instruments power down one by one thing is certain: Venus Express marked a turning point. It showed that even where we thought nothing could be found, mysteries still await to be uncovered. We are in 2010. With relative discretion, the Japanese probe Akatsuki, whose name means dawn, leaves Earth to join Venus. This mission, led by the Japanese Institute of Space Sciences and the Japan Aerospace Exploration Agency, marks a turning point in the exploration of this veiled planet. The ambition is clear: to unlock the secrets of its atmosphere and detect possible lightning with instruments tuned to certain wavelengths. From the outset, scientists are betting on Akatsuki's ability to scrutinize this scorching world, where the surface exceeds 460 degrees Celsius or 860 degrees Celsius, and to elucidate why its atmosphere rotates faster than the planet itself. The launch goes off without a hitch, and the probe embarks on several months of travel toward its target. At the end of that same year, Akatsuki attempts to enter orbit around Venus, using its main engine to slow down. But a fault in the control system causes a critical failure. Unable to decelerate adequately, the probe misses its target and enters an orbit around the Sun. This setback is a heavy blow for the teams, who see the 2010 observation window slip away. A race against time begins to keep Akatsuki operational and prepare for a renewed attempt. Fuel reserves are carefully assessed, components analyzed, and the trajectory gradually adjusted for a future return near Venus. In December 2015, Akatsuki gets a new opportunity. Thanks to a series of precise maneuvers, a smaller auxiliary engine is successfully activated. This time, the propulsion works, and Venus's gravity finally captures the craft. Although its orbit differs from the initially planned one, Akatsuki officially becomes a satellite of the planet. After 5 years of waiting, the relief is immense. The instruments, which had been on standby, are gradually reactivated. From the first ultraviolet images, strange structures appear in the upper layers of the atmosphere, revealing waves whose origin remains unexplained for a long time. The main interest of the mission lies in the variety of instruments on board. An infrared camera tracks cloud formations in the upper atmosphere to assess wind speeds and better understand superrotation, the phenomenon where the air turns much faster than the planet. On Venus, clouds make a complete rotation in just 4 days, while the planet takes hundreds of Earth days to complete one rotation. In parallel, the ultraviolet camera focuses on finer details of the clouds. The contrasts reveal atmospheric waves traveling thousands of kilometers or miles, indicating powerful energy transfers between different layers of the atmosphere. Beyond these observations, another aspect intrigued scientists: the possible presence of lightning. Since the first Soviet missions, the hypothesis of electrical discharges in Venus's dense atmosphere has fueled debate. With extreme temperatures and crushing pressure, understanding storms on this planet helps unravel its complex chemistry. Akatsuki carries detectors capable of recording extremely brief light pulses, hoping to prove the existence of lightning. The initial results are ambiguous, but some signals suggest that storms might occur in the upper regions, despite the absence of a water cycle. Despite the setback caused by its wandering around the Sun, Akatsuki quickly delivers major data. By the end of 2016, researchers published detailed thermal maps thanks to infrared sensors, revealing temperature variations according to altitude. These results help understand how heat circulates in the atmosphere. The ultraviolet images also show stationary waves forming above the terrain, especially during the transition from day to night. Their orientation and stability are intriguing because they reveal that, beneath the thick mist, Venus indeed has mountains and valleys capable of influencing the winds. Over the years, researchers have refined their tools and honed their models. One of the goals is to better understand the role of convection and gravity waves in superrotation. Nighttime infrared images reveal fluctuating bright patterns. These variations, related to the structure of clouds and high-altitude winds, could be caused by volcanic or thermal phenomena still not confirmed. Detecting eruptions remains difficult through the thick cloud cover. Yet, Akatsuki continues to paint an increasingly precise picture of the winds, temperatures, and chemistry of Venus's atmosphere. One of Akatsuki's major assets lies in the stability of its orbit, which allows the mission to be extended well beyond its initial duration. After reassessing its energy capabilities and the state of its instruments, the Japanese agency decides to renew it multiple times. research on lightning continues, with cameras still scrutinizing every corner of the high atmosphere. International collaborations are forming, comparing Akatsuki's data with ground-based observations in the far infrared. This synergy allows identifying periodic variations in superrotation, the causes of which remain to be elucidated. In 2024, despite signs of aging, the probe remains active around Venus. The Japanese Institute for Space Science reports a partial loss of communication, but Akatsuki continues to send images in the infrared and ultraviolet. New orbital adjustments are being considered to extend its scientific mission even further. In the year 2020, an unexpected announcement shakes the scientific community: the possible detection of phosphine in the clouds of Venus. This molecule, composed of one phosphorus atom and 3 hydrogen atoms, is on Earth a product of industrial or biological processes in oxygen-poor environments. Its presence on Venus intrigues scientists because few natural processes are known to produce it in such an environment. To understand its importance, one must remember that Venus is often referred to as Earth's sister due to its similar size. However, its atmosphere is extremely dense, with ground pressure 90 times greater than that of Earth, and temperatures well above 860 degrees Fahrenheit, 460 degrees Celsius. It is mostly composed of carbon dioxide, topped with clouds of sulfuric acid. Yet, at 34 miles, 55 kilometers, above the surface, temperatures are more temperate, which opens the hypothesis, albeit a fragile one, of the existence of microorganisms in this zone. The announcement comes from an international team led by a professor from Cardiff University who used powerful telescopes, including a large array of antennas in the Atacama Desert. These instruments, sensitive to different wavelengths, have detected a characteristic signal of phosphine. This peak in the data has been interpreted as a possible signature of this molecule. The news immediately causes a stir because phosphine is sometimes considered a biosignature. On Earth, it is produced in small quantities by bacteria living without oxygen. The idea that Venusian life forms could have adapted to such a hostile environment captivates the public, enthusiastically relayed by the media. But caution quickly prevails. Researchers re-examine the data and raise doubts. Some believe the signal could be due to other molecules or result from a calibration error of the instruments. Others highlight the statistical analysis difficulties and the need to ensure the signal is not merely an artifact. Part of the debate concerns the observatories used. Data from a high-altitude observatory aircraft are analyzed to confirm the detection. This instrument, isolated from many terrestrial interferences, does not, however, provide a clear confirmation. Some scientists believe a low concentration of phosphine is still possible, while others conclude it was an interpretation error. In response, several teams set out to explore alternative explanations. They investigate whether chemical reactions related to volcanic activity or lightning could account for the presence of phosphine without invoking the biological hypothesis. Others consider interactions with meteoric dust or the solar wind. Each theory requires complex models, and none stands out as obvious. Caution remains essential. Some teams are recalibrating the initial data, while others are re-evaluating the supposed spectral line of phosphine. To come to a conclusion, it becomes essential to obtain independent observations from multiple facilities around the world. Ideally, measurements taken directly from the clouds of Venus would help clear up uncertainties and provide more solid answers. In 2024, a specialized journal plans to publish a detailed synthesis of the entire controversy. This publication aims to explain, in accessible yet rigorous language, all the methodology used to detect phosphine, analyze its signature, and discuss its possible origin. It will highlight the current uncertainty. The discovery is neither firmly refuted nor definitively confirmed. This article should, therefore, provide an overview of theoretical aspects, measurements made from Earth, and the analysis of data collected by spacecraft in orbit around Venus. Between 2020 and 2023, several validation and follow-up programs were launched to delve deeper into the question. Teams proposed improving ground-based radio telescope techniques to once again measure the precise distribution of phosphine in the planet's upper atmosphere. The challenge, to verify the reality of the concentration variations reported in 2020. On the orbital front, some instruments already in place around Venus have attempted to interpret the data collected beyond the visible spectrum, in infrared and ultraviolet. The goal is to determine if other chemical compounds may be associated with the formation or degradation of phosphine. The possibility of sending future missions entirely dedicated to the chemical analysis of the clouds is also being studied. Some specialists are considering inserting balloons or probes capable of taking aerosol samples to obtain a more refined mapping of the atmospheric composition. This would help identify potential tracers indicating geological or biological reactions. Recent technological advances make it possible to design instruments more resistant to heat and corrosion. Nevertheless, the complexity of the environment remains a major challenge. The strong winds move particles over long distances, and the chemistry of sulfuric acid poses a constant threat to any insufficiently protected equipment. In parallel, some research is turning towards biochemistry. Scientists are questioning the ability of terrestrial extremophile organisms, capable of surviving in hot and acidic conditions, like those found in certain volcanic areas, to adapt to Venus's environment. Of course, the presence of sulfuric acid poses a considerable obstacle, but bacteria living in extreme environments at over 90 degrees Celsius, or 194 degrees Fahrenheit, or at a very low pH, have already been discovered on Earth. Exobiology, which studies life beyond our planet, finds here a fertile field for deepening the understanding of life's limits. Despite everything, between 2020 and 2023, no consensus has emerged. Some studies confirm that small quantities of phosphine could persist in the clouds, while others result in negative or ambiguous findings. These divergences illustrate well the difficulties of observational astrophysics, where the slightest inaccuracy can alter data interpretation. It is in this context that the expected publication in 2024 should provide an updated overview, highlighting avenues to explore and persistent uncertainties. The repercussions of this controversy go beyond a debate among specialists. It has highlighted the extent of our ignorance about Venus's atmosphere and underscored the importance of multiplying instruments and approaches to validate any detection of molecules potentially linked to life. Advances in spectroscopy, which analyzes light to deduce chemical composition, thus become essential for better understanding the chemistry of planets. This story also serves as a catalyst for new exploration projects. Small satellites could be deployed to remain in orbit and observe the planet over the long term. Inflatable probes, capable of settling in the clouds, are also being considered to measure atmospheric dynamics on site, collect precise data, and capture particles. The goal is not only to confirm or refute the presence of phosphine, but to understand how chemical and physicochemical processes function in a world other than our own. The question of life, however, remains open. If phosphine is indeed present in significant quantities, and if no geological or chemical explanation can justify its production, then the possibility of biological activity will need to be seriously considered. But before making such a revolutionary hypothesis, researchers will continue to collect solid evidence and repeat their analyses to rule out any instrumental bias. Between 2020 and 2023, the quest around phosphine has been the scene of cross-analyses, passionate debates, and fruitful questioning. In this, it fully embodies the scientific approach, an initial announcement, strong media coverage, followed by a critical examination that, over time, leads to a possible consensus. For Venus, this episode has rekindled interest in exploration and reinforced the idea that a biological secret might still be hiding in the clouds. These years of research have revealed how partial our knowledge of Venus remains. Although very close to Earth, this planet remains mysterious. The presumed observation of phosphine may be a false start, or, on the contrary, a valuable clue. Further analyses will tell us. What is certain is that this twist has given new momentum to Venusian planetology and reignited the enthusiasm for exploring a planet that has always fascinated us. In the year 2024, a major event confirms that Venus is far from being a stagnant planet. Until now, it was thought that its volcanic activity had significantly slowed down for millions of years. But new analyses of data from the Magellan probe, collected in the 1990s, reveal a very different scenario. Thanks to recent algorithms, cross-referencing radar images highlight geological structures compatible with recent eruptions. These results, published at the end of May, have generated great excitement in the scientific community. The radar data from Magellan, long considered sufficient but limited, have been carefully reworked. Using digital comparison methods, several sets of images have been overlaid from different angles. This approach allowed for a refined mapping of the surface and the identification of lava flows that were previously invisible or blurry. May 27, 2024, marks a turning point. Researchers announced the discovery of recent lava fields in two regions of Venus, Sif Mons and Niobe Planitia. These areas, once considered inactive, now show clearer, brighter flows. The analysis suggests that these formations date back only a few years or decades, very little on a geological scale. To grasp the significance of this announcement, we must recall the role of the Magellan probe. Launched in the early 1990s, it mapped Venus using radar capable of penetrating its opaque atmosphere. The images were transformed into topographic maps, revealing the reliefs hidden beneath the thick clouds. From the first publications, scientists had identified large volcanoes on the surface of Venus, but the question of their activity remained unanswered due to insufficient resolution and lack of time tracking. The new analyses, much more precise, now reveal subtle yet significant variations in the terrain. A lava field is a surface of rock solidified after being emitted in a liquid state. On Venus, these flows are likely composed of basalt, like those found on Earth. But the pressure there is 90 times greater than that of our atmosphere, and temperatures are around 460 degrees or 860 degrees Celsius. These conditions profoundly modify how the lava cools, creating unusual textures. The lava fields observed at Sif Mons and Niobe Planitia appear little altered by time. Their radar signature, uniform and crisp, suggests that they were deposited recently. On Venus, atmospheric deposits quickly cover the terrains. Not seeing them on these flows is a strong indication of recent activity. According to some estimates reported by a specialized site, the planet could experience up to 42 eruptions per year. This figure is based on the frequency of observations, the speed of atmospheric deposits, and the size of the identified flows. Small eruptions would probably go unnoticed, while larger ones would remain visible longer. This figure is debated. To estimate a frequency, one must assume certain characteristics of the lava and the atmosphere. These parameters, still poorly understood, allow for uncertainty. Despite this, most researchers think that this number is likely underestimated and that the actual activity could be much more intense. Active volcanism in 2024 implies that the mantle of Venus retains sufficient internal energy. On Earth, this energy is dissipated via plate tectonics. On Venus, the absence of such structures suggests a model of localized renewal, with occasional magma upwellings. The confirmation of eruptions supports this hypothesis. These eruptions also have an effect on the atmosphere. By releasing gases like sulfur dioxide, they influence the air chemistry and reinforce the greenhouse effect. Each volcanic plume could trigger complex reactions with the gases already present. Their study, still ongoing, is essential to better understand the planet's climate. Moreover, the idea of regular volcanism impacts the search for any hypothetical microbial life forms. Even though the surface is in a state of extreme heat, sometimes reaching nearly 470 degrees or 878 degrees, some layers of the atmosphere may offer a less hostile environment. Some models have suggested that sustained volcanic activity could inject substances into the atmosphere capable of supporting a theoretical form of life. A speculative scenario to be sure, but one that has been revived by recent discoveries. Specialists point out that this discovery reinvigorates future missions aimed at exploring Venus. The more volcanic activity is confirmed, the more engineers strive to perfect instruments capable of measuring gas variations in near real time, analyzing the composition of volcanic plumes, and tracking topographical changes. The existence of active volcanism also fuels the hope of observing certain regions, like Sif Mons or Niobe Planitia, where new lava deposits could have recently appeared in a targeted manner. The months following the publication on May 27, 2024, are paced by a series of presentations, conferences, and debates around the evidence revealed by the Magellan reanalysis. Each radar image is examined in detail to trace the flows, measure their thickness, and estimate their density. Comparisons with stable areas allow for better understanding of flow dynamics and magma nature. Some scientists call for new data to be quickly collected on site, while others advocate for maximizing existing archives, pointing out that many visual elements remain to be deeply analyzed. The most striking element is undoubtedly the possibility of up to 42 eruptions per year. This estimate, reported by the media and scientific publications, also raises questions about their power and geographic scope. On Earth, this figure is common, but our planet has active tectonic plates and influencing oceans. On Venus, this frequency takes on a different significance, as the planet is shrouded in thick clouds, and its internal thermal dissipation mechanisms are still poorly understood. The reinterpretation of the Magellan data thus represents a major turning point in 2024. Venus no longer appears as a static world, but as a dynamic planet where heat is released and renews the surface. The lava fields identified at Sif Mons and Niobe Planitia become key pieces in an incomplete puzzle that sheds light on the planet's evolution through the ages. This discovery also reinforces the interest in continuing research to determine if volcanism impacts the dense clouds and greenhouse effect, or if it is limited to regional effects. The surprise also comes from the fact that Magellan's measurements were considered fully exploited for a long time. Few expected that recent algorithms, enriched by machine learning and advanced filtering methods, would reveal new signals. Yet, that's exactly what happened. The reanalysis enabled a much more precise reading of the topography. By reducing interference and refining calibration, it was possible to identify flow edges and geological patterns that were almost invisible before. This scientific renewal reflects a growing desire to consider Venus as an active planetary system where rocks, gases, and heat interact constantly. The new data clearly indicate that the planet continues to transform, perhaps more rapidly than anticipated. The lava fields detected at Sif Mons and Niobe Planitia become open-air laboratories, where Venus's internal energy is on display. Between thermal flows, gas emission, and crust alteration, the volcanism observed in 2024 becomes a central element of our understanding of this neighboring planet. If these estimates prove accurate, they could well alter our vision of Venus's geological history. The idea that the planet experienced long, calm periods interspersed with intense phases would then find solid footing, perhaps suggesting deep processes comparable to those of other rocky worlds. Scientists are counting on future probes specifically designed for Venus to confirm these eruptions, detect new clues in near real time, or analyze on-site the gases released during these events. Such a scenario fuels the fascination for Venus, often described as Earth's twin, even though its evolution took a completely different path. While our blue planet has developed oceans and a thriving biosphere, Venus has become a hot and oppressive world with a barely hospitable surface. Yet, the revelation of active volcanoes in 2024 unveils a more dynamic face. Far from being a static hell, the planet shows it is in constant transformation, relentlessly shaping its plains and landscapes. So it is the new lava flows of Sif Mons and Niobe Planitia that reignite interest in the planet's interior. Hypotheses about the frequency of eruptions, perhaps exceeding 40 per year, attest to the vitality of a world long perceived as inert. In this mid-year 2024, Venus reveals a new aspect of its internal dynamics and establishes itself as a central subject of study for understanding the formation of rocky planets. November 6, 2024, will mark an important milestone for the Parker Solar Probe. Launched in 2018, this mission aims to approach the Sun closer than ever before. To adjust its trajectory and preserve its instruments, the probe performs several flybys of Venus, allowing it to change its speed without consuming fuel. Each pass refines its orbit, protects it from solar radiation, and enables data collection on the planet's upper atmosphere. During this last rendezvous, the probe will use Venus's attraction one last time to launch even closer to the Sun. The date was meticulously chosen. Teams calculated the ideal approach angle for Venus's gravity to modify the probe's speed. At that moment, the The Parker Solar Probe will pass at only 376 kilometers or 234 miles above the surface. This extreme proximity demonstrates the precision of the maneuvers needed to exploit the planet's gravity. Beyond the orbital adjustment, this flyby is also a unique opportunity to probe Venus's exosphere. Thanks to its sensors, the probe will analyze the distribution of particles in the high atmosphere and share these results with the scientific community. The main objective remains to bring the probe closer to the solar corona. To achieve this, it uses Venus's gravity as a gravitational lever. With each flyby, its speed and inclination are adjusted to make it dive ever deeper into the solar environment. The one on November 6, 2024, should provide the decisive momentum to cross a new threshold. Without this strategy, the amount of fuel needed would have been too significant to consider the mission. This passage perfectly illustrates the importance of Venus in the success of this space endeavor. But it's not just a technical feat. This flyby also allows for a better understanding of Venus's exosphere, the outermost layer of its atmosphere. This is where particles become so scarce that they can escape into space. Studying this area helps to understand how Venus interacts with the solar wind and loses certain gases. The probe's sensors, designed to study solar particles, also provide valuable data on the chemistry and movements in this region. This information improves atmospheric escape models and helps to better reconstruct the planet's history. The main instrument for these measurements is SERENA, designed to detect charged or neutral particles near a planet. By analyzing their composition, speed, and density, scientists hope to better understand the atmospheric erosion processes at play. SERENA, adapted for this mission, will also measure the temperature of these particles and their distribution in space. The data will be transmitted to the entire scientific community for use by different laboratories. Compared with previous readings, they will offer a more comprehensive view of the atmospheric variability of Venus. The results obtained are also of interest to those studying long-term atmospheric escape. Over centuries, planets can lose volatile elements due to the solar wind or energetic particles. The exosphere is the pivotal zone where this process begins. Better understanding it helps to trace the climatic changes of Venus. Some researchers believe the planet may have experienced a more temperate climate in the distant past before shifting to an extreme greenhouse effect. The collected data could help clarify this transition. From a technological standpoint, this latest flyby proves the resilience of the Parker Solar Probe's heat shield. Made from an ultra-resistant material, it must withstand extreme temperatures when approaching the Sun. By skimming Venus at a very low altitude, the probe demonstrates that it can maneuver in a challenging environment without damaging its instruments. Each success strengthens engineers' confidence and paves the way for even more ambitious missions. Thanks to Venus's gravitational assist, the Parker Solar Probe continues its journey into regions previously inaccessible. Once the flyby is complete, the data will be analyzed and then made available to specialists worldwide. The initial steps will involve checking the quality of the measurements, then integrating them into databases open to everyone. This will encourage cross-disciplinary collaborations and foster cross-research, essential for deciphering the complexity of Venus. The resulting publications should shed new light on the exosphere and enrich comparisons with other planets. The initial analyses of SERENA's measurements will be quickly utilized by international experts. They will allow for estimating the density of particles in the exosphere, distinguishing simple atoms like oxygen or hydrogen from more complex molecules. This data will complement the numerical models of Venus's atmosphere. By linking them to existing theories, researchers will refine scenarios describing Venus's transition from a potentially temperate world to a planet dominated by an intense greenhouse effect. Thus, this flyby will not only be a technical achievement, but also a lasting contribution to scientific research, beneficial even in the field of exobiology. In 2024, a major turning point is approaching in the quest to understand the planet Venus, often called Earth's twin because of its size and proximity. Until recently, some scientists believed that Venus might have harbored vast oceans several billion years ago. However, isotopic analyses published in December 2024, notably reported by Reuters, have shaken this hypothesis. The samples examined indicate an interior much drier than imagined, suggesting that the planet might never have held large amounts of liquid water on its surface. This revelation challenges traditional scenarios of planetary evolution and renews scientific interest around the habitable zone in conditions conducive to the emergence of life. To grasp the significance of these results, one must first understand isotopic analyses, a key tool for tracing the history of water and other volatile elements. Isotopes are forms of the same chemical element differing by the number of neutrons. By studying the ratios between these isotopes, researchers can deduce if a planet has retained or lost water, even in trace amounts within its internal structure. On Earth, a stable abundance of isotopes is accompanied by a complex hydrological cycle connecting the atmosphere, surface, and subsurface. On Venus, this cycle is absent, and recent measurements reveal no trace of significant ancient water reservoirs. These findings fuel a global reassessment of the planet's geological history. The report published in December 2024 highlights strong past evaporation, coupled with significant losses of light compounds. While on Earth, the water cycle continuously regulates chemical balance, Venus experienced a far different situation. Its surface temperature, often exceeding 400 degrees Celsius, 752 degrees, favored the dissociation of water molecules and the escape of hydrogen into space. The residual oxygen, meanwhile, might have fixed itself in the crust, or combined with other elements. This dynamic suggests a planet incapable of retaining or recycling its water. The isotopic data are difficult to reconcile with the idea of ancient, long-lasting oceans, reinforcing the thesis of a planet that remained dry. This upheaval in our perception of Venus leads to a revision of the very concept of the habitable zone. For a long time, its proximity to Earth placed it in a region deemed favorable for liquid water, but reality appears more complex. Distance to the star is not enough. Initial chemistry, volcanism, and the ability to maintain a protective atmosphere are equally decisive. The results of 2024 tend to confirm that Venus, despite its position, probably never met these conditions. This finding prompts astronomers to reconsider the criteria for exoplanet habitability, emphasizing that orbit alone does not guarantee a life-friendly environment. However, some researchers remain open to the idea of a brief wet period in Venus's history. If the planet had received water early in its formation, it could have quickly evaporated under the intense greenhouse effect caused by an atmosphere very rich in carbon dioxide. Hydrogen would have then escaped into space, while oxygen would have been absorbed by the crust. The 2024 measurements are compatible with this hypothesis of rapid desiccation, although consensus leans towards a very brief duration, reducing the likelihood of a sustainable environment. This perspective redefines the debate on a habitable Venus, instead suggesting transient and unstable conditions. The implications of this new image of Venus also affect its tectonics and internal evolution. On Earth, water facilitates subduction and continental drift, contributing to geological and climatic stability. In the absence of water, Venus would have experienced limited tectonics, leading to an accumulation of internal heat and potentially very active volcanism. Observations from missions like Magellan reveal vast basalt plains and complex structures, evidence of this volcanism. Recent isotopic data confirm that these eruptions were not based on deep hydric exchanges, which could explain the planet's peculiar physiognomy. But beyond the question of water, these studies also focus on how Venus has trapped or lost various chemical elements. Isotopes allow scientists to assess a planet's ability to retain or release light elements, such as hydrogen or helium. The dense and hot atmosphere of Venus favors intense reactions, accelerating these processes. Studying these mechanisms offers a better understanding of the diversity of planetary atmospheres. If Venus turned out to be almost dry from the beginning, its status as Earth's sister must be nuanced. The upcoming missions scheduled after 2025, notably more advanced atmospheric probes, will refine our understanding of its chemistry and dynamics. The December 2024 announcement thus highlights the importance of comparisons between Earth and Venus to understand why two planets with similar characteristics have had such different destinies. Earth benefited from an optimal distance from the Sun and a protective magnetic field, preventing the thermal runaway observed on Venus. Plate tectonics and ocean circulation have trapped some of the carbon dioxide in Earth's crust, limiting warming. Venus, on the other hand, seems to have accumulated conditions favoring water loss and uncontrollable warming. Specialists see it as a warning about the fragility of climatic balances. In light of these discoveries, the concept of a habitable zone requires a deep overhaul. Observations of distant worlds show that orbital position is not enough. Parameters like initial chemistry and geological activity can turn a promising environment into a burning desert. The results obtained between 2024 and 2025 on Venus indicate that only a precise understanding of isotopes and internal processes will allow us to identify true habitability. Venus teaches us that not every body in a habitable zone is necessarily a refuge for life. At the dawn of 2025, the exploration of Venus is set to reach a new milestone, with several ambitious missions in the pipeline. For decades, space agencies have been refining their instruments, optimizing their flight strategies, and multiplying international collaborations to better understand our neighbor. Teams are doubling their efforts to fine-tune every aspect, from sensors to launch schedules. Several projects are already taking shape, promising to unveil the atmosphere, composition, and geology of Venus. Among them, the Venus Life Finder program, developed by Rocket Lab and MIT, focuses on the temperate layers of the Venusian atmosphere. Scheduled between 2025 and 2026, this microprobe will try to detect chemical signatures potentially related to a form of metabolism. The idea is to check if some unexplained compounds can accumulate in the least hostile zones, where temperatures hover around 50 degrees Celsius or 122 degrees Fahrenheit. Although the extreme acidity of this atmosphere makes any biological scenario highly speculative, the slightest trace of a relevant molecule could upend our perception of life in the solar system. Another flagship mission, Da Vinci, led by NASA, with a launch planned in the 2030s. This probe will plunge into the Venusian atmosphere between 2031 and 2032 to collect chemical data from the upper atmosphere down to the ground. It will analyze noble gases, among other things, to trace the planet's history and compare it to Earth's. It will also provide detailed images of the surface, revealing local morphology and traces of geological activity. Protected by a heat shield, Da Vinci will have to withstand temperatures exceeding 400 degrees Celsius or 752 degrees Fahrenheit and extreme pressure. Its goal, to surpass the performance of the old Soviet Venera probes. In parallel, the Veritas mission, also led by NASA, aims to map the surface of Venus with unparalleled precision. Postponed to 2031, this mission will use radar, infrared, and spectroscopic technologies to analyze the topography, gravity, and geological composition of the planet. Through this detailed mapping, scientists hope to spot signs of recent volcanic activity and better understand Venus's internal structure. This wealth of data will enable the creation of a comprehensive portrait of the geological diversity of Venus and shed light on the reasons for its evolution so differently from that of Earth. The European Space Agency, known as ESA, is fully engaged in this scientific dynamic with the Envision mission. This next-generation orbiter will follow previous explorations of Venus. Officially adopted in January 2024, it will be launched in November 2031. Envision will carry an array of radar and spectroscopic instruments designed to observe the surface with extreme precision and analyze atmospheric movements. One of the main objectives is to offer a global mapping, from studying cloud systems to detecting the slightest crustal deformations. Thanks to a sophisticated radar, the mission could reveal potential tectonic activities or imperceptible landslides. For decades, the scientific community has been questioning the possibility of active volcanism on Venus, and Envision could provide solid answers. Looking at the timeline of these missions, an ambitious schedule is emerging, promising by the end of the 2030s a true revolution in our understanding of Venus. Venus Life Finder will look into possible signs of life in the clouds. Da Vinci will explore the transition between the high layers of the atmosphere and the surface, while Veritas and Envision will focus on geological analysis, internal structure, and possible dynamic movements. By combining these approaches, it may be possible to unlock the mysteries of Venus's distinct evolution from Earth, despite having similar origins. These missions demand rigorous coordination, funding spread over several years, and the combined expertise of many specialists: engineers, planetary scientists, physicists, chemists, and space navigation experts. Technological advances today allow the miniaturization of instruments while strengthening them against extreme conditions, temperatures exceeding 752 degrees Fahrenheit, 400 degrees Celsius, and pressures equivalent to those of Earth's abysses. This robustness makes longer missions and richer data possible. Communication systems have been refined to transmit large amounts of information through the thick cloud cover, paving the way for more comprehensive exploration. The general public will follow each step, from laboratory tests to launcher preparation. Every major announcement, every hint of geological activity or atypical molecule will garner keen interest, both in the media and among enthusiasts. The data will be compared, cross-referenced, analyzed, to confirm or refute the proposed hypotheses. This rigorous process will allow validating the most promising leads or ruling out others. In space, the challenges are immense. Venus Life Finder will have to evolve in the upper layers of the atmosphere, a more forgiving zone, but traversed by acidic and violent winds. Da Vinci, on the other hand, will have to plunge to the ground, requiring a thermal resistance system and instruments capable of operating in an extreme environment. Veritas will need to stabilize its orbit to map the planet in very high definition, which implies regular adjustments and precise energy management. Envision, finally, will need to synchronize its observations with those of Veritas to provide an overview, from the atmosphere to the internal depths. All these strategies aim to fill gaps in our knowledge of Venus, but also to prepare for the study of exoplanets that resemble it. The data will be disseminated globally, creating a vast virtual laboratory where scientists will pool their analyses. This close cooperation between ESA, NASA, and private partners like Rocket Lab illustrates the importance of pooling resources to tackle such complex challenges. If everything goes as planned, the 2030s will deliver unprecedented precision measurements of Venus's atmosphere, surface, and interior. It will take time to interpret these data, but the wait is justified. Venus remains a fascinating enigma, similar to Earth in size and initial composition, yet it has become a scorching world. Questions related to the possible disappearance of an ocean, the absence of a global magnetic field, or the impact of volcanism will be at the heart of future research. The year 2025 will mark the beginning of a critical period. The program will start with the Venus Life Finder, which will analyze the clouds for chemical signals. Then, around 2031 and 2032, Da Vinci will dive into the atmosphere to study its composition and take images of the surface. Meanwhile, Veritas will map the planet with a next-generation radar. Finally, Envision will be launched, offering an overview with the most advanced techniques. Each mission is part of a progression logic, where initial observations will guide the following ones. Discoveries of this decade will define the future exploration directions. If active volcanism is confirmed, its effect on heat distribution will need to be understood. If unknown molecules appear in the clouds, their nature will need to be elucidated. And if the surface turns out to be more complex than expected, this will open new perspectives on the comparative history of Earth and Venus. While awaiting these answers, teams from MIT, Rocket Lab, NASA, and ESA are working hard to keep the schedule. Revealing the secrets of Venus also means better understanding our solar system and possibly other worlds like it. The adventure is just beginning. The period from 2026 to 2035 could well become the great decade of Venus. These years will see intensified cooperation between American and European space agencies around ambitious missions intended to explore the hottest planet in the solar system. The goal isn't limited to unraveling the mysteries of its atmosphere. It's also about exploring its geology, spotting potential volcanic activities, and reconstructing its climate history. Behind its dense clouds, Venus may still hold fundamental answers about the evolution of rocky planets. At the heart of this scientific alliance are three complementary missions: Da Vinci, Veritas, and Envision. Each plays a specific role. Da Vinci will descend through the clouds to collect gases and take descent images. Veritas will focus on high-resolution topography, thanks to advanced radar techniques. Envision, led by ESA, will study internal geology and seek traces of recent tectonic movements. This cross-approach will allow for immediate data sharing. Da Vinci's measurements will reveal the chemical composition of the atmosphere, while Veritas will identify reliefs and geological formations. Envision can then confirm or nuance these results by combining its own radar and spectral observations. Together, this information will outline a coherent picture of Venus's evolution. In parallel, Innovative ideas are taking shape. Some laboratories are considering deploying seismic sensors on balloons. Others are developing gliders that could fly over the planet at long distances, or solar sails capable of making rapid round trips. These concepts push the limits of exploration on a planet where heat regularly exceeds 460 degrees Celsius or 860 degrees. This intensive program is expected to result in a wealth of discoveries by 2035. The study of violent winds and cloud structures will offer new hypotheses on atmospheric dynamics. Geology, on the other hand, could reveal the existence of still active volcanoes, and radar data will allow for the analysis of reliefs, faults, and circular formations known as coronae. The idea of microbial life, although controversial, remains explored. In the upper layers of the atmosphere, the temperature drops to about 60 degrees or 140 degrees, which fuels bold theories. Upcoming instruments will analyze the mists to detect any chemical anomalies. If biological activity were detected, even minimal, the impact would be considerable. Whatever the outcome, exploring Venus enriches our understanding of extreme environments. This research is part of a broader goal, to study exoplanets similar to Venus. Around other stars, some planets lie in a zone where a runaway greenhouse effect can emerge. This is referred to as the Venus zone. The data collected about our neighbor will help refine climate models used to understand these distant worlds. The TRAPPIST-1 system is a good example. Its rocky planets, some of which are located in the habitable zone, may have experienced divergent evolutions. TRAPPIST-1c in particular intrigues scientists. The detailed analysis of Venus will serve as a comparison point to assess whether this exoplanet can retain water vapor or not. Even without direct observation, each advance on Venus will help interpret signals coming from these distant worlds. On a technical level, testing tools on Venus helps prepare for future missions to other extreme planets. Airborne seismometers, solar sails, and heat-resistant materials will open up new possibilities. This decade will also form a new generation of engineers and researchers skilled in the challenges of robotic exploration in extreme environments. By studying this world so close yet so different, we get closer to answering a fundamental question: how does life emerge in the universe?